So are you happy now?
Yes, Doctor, thank you so much.
Okay, so we now have what we refer to as spatial resolution. And as you would understand, as you can see, spatial, it's about space. What is the, I need somebody to mute, somebody is, we're getting feedback from somebody. Okay. Yeah, so when it comes to spatial resolution, we are talking about the smallest distance that, smallest area that can be measured. And spatial resolution can range from, spatial resolution can, the highest spatial resolution we have is 30 centimeters, and it can range up to 1 kilometer. So this is the pixel size that you would want to consider. Yeah? So different satellites will have different spatial resolution. And there is a way in which spatial resolution and temporal resolution have what we refer to as an inverse. We have what we refer to as an inverse relationship. So the higher the temporal resolution, the lower the spatial resolution. So for example, we have a sensor called MODIS. It has a spatial resolution of 1 kilometer, but it has a temporal resolution of 1 day. Yeah, so yeah. Can you see my whiteboard? I've stopped.
It has gone off.
Okay, can you see the whiteboard?
Yes.
Yes.
So what we're saying is that we have so what we are saying is that we have what we refer to as an inverse relationship. So as spatial resolution increases, temporal resolution reduces. So these are things that we need to appreciate, that as we improve spatial resolution, temporal resolution usually goes down. The other thing that we also need to appreciate is that as temporal resolution improves, we now start moving from free to paid for data. So many of your lower spatial resolution images are free. And as we now start going towards spatial resolution of 1 kilometer and 1 meter and above, we now need to start paying for, we now need to start paying for the service. Yeah. So back to our slides. So we have talked about what we refer to as temporal resolution. We have seen spatial resolution. We also have what we refer to as radiometric resolution. And I will describe this with in the next slide. When you talk of radiometric resolution, we are talking about quantization of, we call it quantization of energy. So what are the possible values that your pixel value can have? So for example, as you can see here, if you had a 2-bit image, it means that your image would have 4 values, 2 to the power 2, which is 2 times 2, which is, so your dynamic range would be from 0 to 3. And your darker pixels would be 0, and your brightest pixels would be 3, and anything in between would have those values. As you can see in the, you can see there's that matrix where you have 1, 2, 2, 0, 1, 3, 2, 0, 3. Of course, the zeros would refer to the dark pixels, and the white would be 3, and your values would range from 0 to 3. If we had a 3-bit image, it means that we would have each pixel value has a potential of 8 grayscale values, ranging from 0 to 7, as you can see on that image. We have 1 0 0 0 0 2 1 4 4 7. So 6 and 7 don't seem to be very different on screen, but the 7 would be the brightest. However, for most of many of our images, we are dealing with 8-bit images, and that means we have 2 to the power 8 levels. So we have 256 levels. So each pixel value can range from 0 to 256. And our dynamic range will be from 0 to 255. And we'll be seeing this in detail when we resume discussion of our remote sensing process. We shall come here and and appreciate it better. So going back, we have seen temporal resolution, we have looked at spatial resolution, we have looked at radiometric resolution. We are going to look at spectral resolution in a short while. I request that we wait a little. And before you is a satellite image. Can somebody guess where that is?
Makerere, part of it.
That is Makerere.
Yes.
Now, from your various backgrounds, what do you think we can apply this image for? If you have this sort of snapshot, what do you think you can use? What are the sort of applications you think you can use for this?
Transport, for maybe tourism for navigation of directing someone to a new place, to a new location, if you're using maybe a map.
All right, very good. So one of the applications can be transport navigation, because we have locations, we can tag those locations, we can come up with routes to those places. That's a very good example. Any other ideas?
And to find out the built-up area vis-a-vis the green area within the campus.
Yeah, so we can use it for physical planning. We can map the areas, the built-up areas. We can distinguish slum areas from, maybe not slum, we don't say slum, we call them informal settlements from the formal settlements, as you can see. We can even map out areas. We can do, because you can carry out a topographic survey of this area. The only challenge is that you may not have the contours, but you can get the contours from a digital elevation model. You are GIS professionals, you know what a digital elevation model is, and from the digital elevation model, we can extract contours, which we can now append to an extract of this area. So we can digitize. By now, you should know what digitizing is. You can digitize the buildings, you can digitize the roads, you can digitize the informal settlements, we can digitize the green areas, and together with the digital elevation map, we can come up with a topographic survey of this area. Many of you are surveyors. You would know how long it would take you to carry out a topographic survey of this, whether you're using RTK or you're using a total station or a T2. I don't know if you people still use T2. It may be too old for you. But yeah, those are some of the applications that you can use this for. Now, when you look at this, what are some of the things that you can make out of this? There's a point I want us to discuss. You see Sapol Kagwa Road?
Yes, yes, we can see it.
You can see the road connecting from Sapol Kagwa to Kasuvi. Is it one person seeing, or they are all? You can all see it.
We can all see, Doctor.
What is the nature of that road?
The nature right now, it is tarmac.
But what was in the image?
Maram.
The image shows Maram.
So the point I want to bring out is that when we're dealing with the remote sensed imagery, it's very important that we also consider the currency of the image. So because the satellite image is showing a Maram road doesn't mean that it is wrong, but it was accurate as at the time the image was collected. Are we together? Yeah. So when we're dealing with imagery, especially when you're looking at the temporal aspects of the imagery, with the other aspect that is equally important is how current is the image. Going ahead, I'm hoping that you can think of various applications. We have numerous applications of satellite imaging. Whenever I'm teaching, I actually say that in terms of applications, we are only limited by our imagination. What you're seeing here is not all that we can do. As you can see in the clip, we can use satellite imagery for earthquake monitoring. We can monitor the impact of earthquakes. We can do deformation monitoring. So for example, we have got, we're going into oil exploration. Oil will be sucked out of the ground. And in other places, as you can see here, we have land subsidence. There's a very real possibility of the land subsiding in many of those areas. So we can monitor that using remote sensing. We can do urban monitoring, we can do flood mapping, and there's a whole host of possibilities. And hopefully, time permitting, we shall also be able to get some people come and share the work they have done. Now, I am hoping that you can begin thinking about some of the advantages and challenges that come with acquiring information in this way. Yeah, so I want after this to play a video, and some of you may have watched it, most of you may not have watched it, but I want you to pay attention to this, and I want you to, let me probably post these questions on, yeah, let me post these questions on yeah, let me get these questions and post them in the chat so that you can think of them as we play the video. Okay, so let me get
And we have liftoff. And we have liftoff.
Space exploration was once the preserve of big governments spending big bucks. But as satellites have become more commercially interesting, the heavens are really beginning to open up. A new space age has begun with ordinary companies.
Sorry, we lost network. Were you able to see that? I'm going to start afresh.
Yes.
Okay, let's start afresh.
And we have liftoff.
Space exploration was once the preserve of big governments spending big bucks. But as satellites have become more commercially interesting, the heavens are really beginning to open up. A new space age has begun with ordinary companies venturing up into the skies. These are the real galactic frontiersmen. But how do they do it? When you think of rural England, you might think of rolling hills, cows, and cups of tea.
Sorry, we seem to be having internet challenges. Let's try again.
And we have liftoff.
Space exploration was once the preserve of big governments spending big bucks. But as satellites have become more commercially interesting, the heavens are really beginning to open up. A new space age has begun, with ordinary companies venturing up into the skies. These are the real galactic frontiersmen. But how do they do it? When you think of rural England, you might think of rolling hills, cows, and cups of tea. You might not think of satellites. But buried deep in southern England is Surrey Satellite Technology Limited. It may not have the scale and grandeur of NASA, but then these guys aren't bankrolled by billions of taxpayer dollars. These guys are doing it for themselves. Since 1981, they have designed, built, and launched over 30 satellites into space. The key to that success is not spending money, as MD Dave Hodgson explains.
Our satellites typically cost tens of millions of pounds. This compares with a traditional space industry cost of hundreds of millions of pounds.
3, 2.
Satellites are expensive because they're filled with highly sensitive scientific instruments that have to survive being blasted 700 kilometers into space, where they'll spend years being bombarded by cosmic radiation and exposed to the searing heat of the sun. In spite of these challenges, in Surrey you can get fixed up with your very own satellite from as little as $10 million. Bargain. The key to keeping the cost down is their use of off-the-shelf technology. Everything from insulation tape to the same kind of computer chips found in your laptop. These highly skilled aerospace engineers have a down-to-earth approach to space.
These are the sorts of things that we will make slight modifications to and launch and fly in space.
But not everything you need for your own homemade spacecraft can be bought at your local hardware store. The satellite they're building will be part of the Disaster Monitoring Constellation, or DMC, capturing vital images within hours of natural disasters, enabling relief agencies to identify where help is most needed. But to respond to everything from tsunamis to tornadoes, it has to be able to take crystal clear pictures from 686 kilometers above the Earth. For that, you need to spend some serious money and go bespoke. And there's nothing cut price about the state-of-the-art imaging systems that they build from scratch on site. The snappily named multi-spectral imager is assembled by hand in an ISO Class 6 cleanroom, a filtered environment completely free of dust. Consumer cameras can give you images of 12 million pixels. The multi-spectral imager is capable of recording more than 8 billion pixels. That means in a single snap, it could capture an image of 300,000 square kilometers, an area the size of Italy. But black and white satellite photography went out with the Cold War. These days, we like to see our planet in color. So, 3 ordinary color filters combine to produce an ordinary color image, as seen by the human eye. While another, extraordinary infrared filter captures what the human eye can't see. In an infrared image, water like Lake Michigan shows up as dark blue or black, while in greener places, vegetation shows as vibrant red. But will this million-dollar camera survive the violence of a rocket launch and the rigors of life in orbit? Time for some space shock simulation. First up, this reinforced steel chamber, which can replicate the vacuum of space. Then, this temperature chamber, which can heat the components up to 120 degrees Celsius and chill them to minus 100. Once a satellite's passed its tests, there's just the small matter of getting it into space. Now, you might think launching a satellite involved all this palaver. Boosters, auxiliary thrusters, and expensive manned missions. But by far the most cost-effective way to get anything into orbit is sticking it on the end of one of these, a converted Russian intercontinental ballistic missile. Launches always draw a great crowd. Nothing more exciting than watching rocket fuel burn. Once it's in orbit, the pixel-perfect pictures produced by the satellite will be used for everything, from life or death emergencies to monitoring crops and urban planning. And thanks to these plucky pioneers, conquering the heavens no longer costs the Earth. 20,000 roses are picked every single
Sorry, I have just seen the request for volume. Unfortunately, it was on the maximum volume. However, I can get you the video when you come for the rest of the recordings. Yeah. So to our buzz questions. You saw them there. So in which country and town is this satellite being built?
Southern England.
It's built where?
I had Southern England.
Yes, Southern England. Where specifically? Yeah, so it is in a place called Surrey. That's in England. And yeah, it's a village in one of those village places, but it also has a famous university there. And what's the company? What's the name of the company building the satellites? I already even told you the it is SSL, the Satellite Company. So when did they start building satellites?
1981.
Are you sure? How much does it cost to send? What is the cost of sending the satellites to space?
$10 million.
Yeah, it's in tens of millions of dollars, as opposed to the NASA ones, which are hundreds of millions of dollars. So, and as you saw, they use regular equipment, they use regular staff. In South Africa, there is a university called Stellenbosch. They also built their Earth observation satellite, and they launched it into space. And yeah, apparently Uganda were also doing something similar. We are waiting to see what our satellites will look like, but it was also being assisted by the Japanese. So, but also the Chinese have been helping a couple of countries. They've helped Ethiopia build their Earth observation satellite. And yeah, we're waiting to see where all these will end. And what's the main application of this sensor?
Disaster monitoring.
Yeah, disaster monitoring. So they have what they call a disaster monitoring constellation. And as you heard, they have built more than 30 of these satellites. So there are these collection of satellites, call them a constellation of satellites that are orbiting. If you hear of Nigeria Sat, it's being built by this company. So Nigeria has got a couple of satellites. I think Nigeria Sat 1 and 2 or 3. And so it was this company which built for them the satellite. I think probably also the Algerians, I don't know who else. So yeah. So at what height do the satellites operate? Does anyone remember?
686 kilometers.
Okay, 686 kilometers. So that is where our satellites are orbiting and collecting information about the Earth's surface. Let's get back to my, So what happens is that if this is our Earth, and we have your satellites operating there, they're collecting information about the Earth's surface. We refer to this as the swath. And usually the lower your satellite is to the Earth, the higher the spatial resolution, but that means also the lower the temporal resolution. So you have your other satellites which are higher up in space. And as the swath increases, also the spatial resolution decreases. And then, of course, you have those which are much higher. So the lower the satellites, as you can see, the smaller the swath, but also the higher the spatial resolution. And so the lower the satellite, the higher the spatial resolution, but also the lower the temporal resolution. So you will have, for example, your very high spatial resolution imagery. Usually this swath is quite small, but then, so here you can have your high spatial resolution. But now when you start going to Landsat, your swath is also longer, like 80 kilometers. It's around 80 kilometers. And then when you come to MODIS, you can have almost 2,000 kilometers. So, and that means that when you want to do, say, urban studies, where we need to know where the buildings are, we need to have an appreciation of those details. There, you will need to use a higher spatial resolution. But now, if you want to study more at a regional scale, maybe your Landsat would be more appropriate. And now, if you also want to now study something, let's say you want to look at land cover dynamics in the East African region, maybe you will want to use the 2-kilometer swath imagery, which will have a low spatial resolution of 1 kilometer, but at least we're collecting information daily. So, for example, one of the applications to which I have used MODIS imagery is monitoring water quality of Lake Victoria. Time permitting, I'll talk about it. But why I am, let me just put another whatever. I'm trying to see how we can monitor water quality on Lake Victoria. If I was to use Landsat imagery, if your lake is around 300 kilometers, here it's almost around 200. If I was to use Landsat, you can see that I would need many images. Of course, they don't look like that, but this is for illustration purposes. If I was to use Landsat, that's what I would have to use. But when I use MODIS, MODIS covers a huger area, and I'm able to look at the lake at one go. So whereas Landsat would give me higher spatial resolution data, I would need so many images collected over different days, and that would also be a challenge. But I'm now we've used MODIS. Yeah, so I have contrasted, sorry. So let us say I have contrasted the Landsat, one of those that you'll see, and MODIS imagery. So Landsat is the one which would be these various Shame, seems are you there?
Yes, we are present.
We seem to have lost the image. So what I was saying is that if we have Lake Victoria, if we had Landsat, would have needed many images to cover the whole lake. MODIS, we just need to get one because the swath the swath covers the whole lake at once, most of the times. So sometimes when we're choosing the imagery, we need to make a trade-off between what we want to cover, between the spatial resolution, the coverage, but more importantly, the application. So back to reflecting on where we were today, where we started. We began the day looking at, we say that we have satellites which are orbiting the Earth, and they are collecting information from the Earth's surface. This information has to eventually come down from the satellite, and it is captured by a ground receiving station, and after it has reached the ground, we will do some pre-processing, and we shall be looking at some of these pre-processing methods. And then after that, we have our various applications. We have said that our satellites have a need for a source of energy, and one of the predominant sources is the sun. And what happens is that we have sun emitting energy, electromagnetic energy. We have interactions in the atmosphere, interactions on the Earth's surface. We have the satellite, which captures the energy. We have had a reflection on how those satellites operate. This collected information will eventually have to come down to a ground receiving station, and yeah, we'll have to come back down to ground receiving station. And after that, we shall have pre-processing, and then we have applications. So tomorrow, we want to start by discussing, because when we're talking about energy, we're essentially talking about electromagnetic energy. Some of you last did study about electromagnetic energy when you were dealing with physics at A level, or maybe physics at campus. So what is essentially being transmitted from the sun through the atmosphere to the Earth's surface to the satellite is really electromagnetic energy. So we shall be looking at electromagnetic energy, what it is, its properties, and once we have an appreciation of electromagnetic energy, we shall now discuss the energy interactions in the atmosphere. We shall discuss energy interactions on the Earth's surface, and we shall see what implication it has on what is captured, how it is captured, but most importantly, how all of these energy interactions in the atmosphere, energy interactions in the Earth's surface, how they guide us in applications. So yeah, that is it from me today. I wonder if we have any questions. Oh yeah. Oh, good. Someone has reminded me. Spectral resolution. From the clip, how many cameras? Just a minute. When we were, thank you for reminding me, this on and off made me forget. There's this question, how many cameras did we see in this satellite? Uh-huh, 4?
Yes.
Any other suggestions? Are we all convinced that there were 4?
Yes, there were 4.
Yeah, you are actually right. There were 4. Remember, they said that for blue, green, red, and near infrared. So there are 4 cameras, and actually, the number of cameras is what determines spectral resolution. Yeah, so as you can see, we've looked at temporal resolution, spatial resolution, radiometric resolution, spectral resolution. We shall appreciate it later on, but ultimately, when it comes to spectral resolution, we are talking about the number of cameras that we have to collect energy. So for these satellites, there are 4. Other satellites will have different spectral resolutions, and it just means that they're collecting energy from different portions of the electromagnetic spectrum. And we shall be looking at that. I just want to play a final video based on somebody saying that they cannot enroll for I'm not sure which one you cannot enroll for. Is it for the ISA module or for the Mwele module? I'm not so sure what you can't enroll for, so you need to tell me. So,
excuse me, Doctor.
Please go ahead.
When you try to enroll on Mwele, you are told that you cannot enroll yourself in this course, and usually that would mean that you would have to allow us to enroll.
Are you using a Makerere email?
Yes, I am.
It should, because everyone has been enrolling. Okay, I'll look at it and see. By tomorrow I should have an answer. So there's a short clip, really an overview of what we have been doing and what we hope to look at. It's just around 3 minutes, so if the network does not malice us, we should be able to appreciate it.
Welcome to the European Space Agency Earth Observation from Space, the Optical View Massive Open Online course. ESA is developing a fleet of satellites to observe and monitor the Earth. The data processed and distributed from those satellites are freely available for science use, services, also for decision makers.
We are in the midst of a sensing revolution. We never had so much data. It tells us a lot of things about the Earth that we didn't know. It provides new insight, not only for science, but also for applications, serving our society, understanding how the Earth operates as a system, and also delivering the new generation of information services.
This course is about optical remote sensing. That means looking at satellite data between the visible and the shortwave infrared. It's this part of the spectrum that encompasses the living bit of the Earth's surface, the bits that are growing, the plants, the phytoplankton, the agriculture, the forest. Technology for acquiring image data at higher and higher spatial and temporal resolutions, finer and finer detail, has dramatically improved over the past decades. And that's enabled remote sensing to explore and understand parts of the Earth system, to measure change, land use, agricultural applications, forest applications, ocean applications.
The optical domain is very natural. People can understand it. It's going from fishery management to food security, energy management. This is really where the light is meeting the life, so we will have incredible insight from space into how our planet is a living organism, about the carbon cycle, about phytoplankton in the ocean and vegetation on the land, and how these two interact as a coupled Earth system.
Now we've got the capability to collect data digitally and almost instantaneously transmit it to the Earth. Optical Earth observation technology is enabling new applications like urban planning, monitoring of vehicles, mapping of building heights in urban environments like this, monitoring humanitarian movements, or looking at detailed changes in the environment that might affect wildlife.
What is really unique about Earth observation is that it touches many disciplines, and it's a kind of integrator around one common objective, which is understanding our planet. You get the global picture, but also the level of details, but also to use this information to support decision making.
The simple objective of this course is to demystify the use of Earth observation data. We will guide you along these 5 weeks of this course through the generation of the imagery. We will explain to you how the data are distributed, how they can be accessed, and how they can be handled. You can learn at your own pace, and also you will have the opportunities to have hands on the data, how to practically work with the data and derive relevant information from 40 years of imaging the Earth. We look forward to you joining this course, and we sincerely hope that you will understand how we can derive really useful information from satellite data.
Okay, so that is just a reflection of the sort of the breadth and width of applications that we can apply remote sensing. We cannot exhaust them. We do not have the time to go through all of them, but I'm hoping that in this week you will have been tickled enough to pick an interest in remote sensing and explore ways by which you can apply it in your various domains. And so I'm going to give you your first coursework. As we go through this, I expect you to be developing it, and your coursework will be to come up with an application relevant to your workplace that you can apply remote sensing. So I want you, as we go through the studies, write for me 2, 3, 4, 5 pages about how we can apply remote sensing to where you are working. So you'll need to describe to me the work that you're doing, how you know, and then yeah, and this cuts across whether you're a valuer, you are a planner, you are a surveyor at UNRWA or KCCA or whatever it is, just one application. You may be in a place where they're having more than one application. Just pick one to describe what you are doing. Are we together?
Doctor, pardon on that. Do you want us to have like several applications or just one application written in, like write about only one application or several applications?
Wherever you're working, you write about one application of remote sensing to where you are working. So like I've said, if you're in KCCA, there might be 10 possible applications, but you just pick one. Is that okay?
Yes, it is.
Yeah.
Yes,
so regardless of where you're working, and if you have 3 people working in KCCA, I don't expect you to write about the same thing. So yeah, pick an application and describe how we can use remote sensing to address that. Any questions? Okay, if there are no questions, we shall resume our class tomorrow at about 5:30. Thank you very much.
Thank you, Doctor.